I drop entropy like E40 slang. You prove or crash, that's bang, bang, bang. Claim you're plonk, but you're just confused. Circuit sloppy, benchmarks bruised. Back end looking janky like scraper paint. Mainnet run, nah, it ain't. Verifier gone, ghost in the shell. Another zkVM bit farewell. Prover crying, CPU frying, tweeting copium. Whole team's lying. Docs still say alpha release. Proof labs.
Welcome everyone. We're going to get started very, very soon. We're 2 minutes past the hour and we have 100 people connected. We'll get started just as this song ends.
RIP to another stack. We out here killing dreams. Yada da me. Bay Area, high fee.
Okay, welcome everyone to Ethproofs call number 5. This call is dedicated to native rollups, and we're going to have Luca Dono give the main presentation. Luca has been working very hard and doing a fantastic job on native rollups, so looking forward to his presentation. Before that, we have a few short updates. So let me just share with you the agenda real quick. And by the way, if you haven't joined the Ethproofs community Telegram group, I do encourage you to join. There's about 500 people. It's not too noisy, and there's a bunch of alpha shared there as well. So far we've had 4 calls in 2025, and this is our 5th one with Luca. And I'm hoping to be able to squeeze 3 more calls this year, one on the $1 million proximity prize, which is relevant to the vast majority of zkVMs, then a call on formal verification, and then finally a call on RISC-V alternatives. And this is today's agenda. So we're going to have 9 different updates, starting from Felix Lee, who will be talking about a new zkVM, which is announced on this call. So Felix, the floor is yours.
My screen?
Yeah, we can hear you, but if you could speak a little bit closer to the microphone, we can't hear you very loudly.
Okay. Thank you for your introduction, Justin. Hello, everyone. I'm Felix from AntChain OpenLabs. Today, we are saw our works on zkVM. In recent years, a series of zkVMs has cut Ethereum block time from hours down to seconds. Since these zkVMs have done such great works, we found some challenges which may be bottleneck towards real-time proving error. For the emulator, we found the code translation and trace generation is the bottleneck, since some parts must be executed in parallel. For proving system, take stats and soundtrack advance rapidly, but entity and extension field computation may be the bottleneck. For recursive proving, current protocols are relative codes, only allowing aggregation of their own generated proofs, and cannot use the proving power of others. For GPU acceleration, operations restrain GPU acceleration due to PCIe transfer bottlenecks and limited GPU memory bandwidth. We found some points that can further help zkVM. Just to emphasize, this is still an ongoing work. For the emulator, we use an aggressive static binary translator to turn RISC-V OP code straight into machine code and a GPU native trace generator to build traces in parallel. That gives us a 6 times speed up. For the proving system, we use base field only soundtrack to scale costly field extension plus an FI in the middle protocol to speed up rotation. That gives about a 60% speed up. For recursive proving, we will build a unified recursive method that can aggregate proof from different protocols, so we can use all esteemed proving network powers. For GPU acceleration, we've designed a multi-GPU hierarchical pipeline that will work by block and shards across GPU to maximize the resources used. Here is the benchmark of our MVP version. For the roadmap, we will finish the GPU acceleration and launch in Java testnet this season. And in next season, we will launch in Java mainnet and implement the unified recursive protocol. About Java, Java is an Ethereum layer 2 that went live on mainnet yesterday. Thank you.
Okay, thank you, Felix. Any questions from the audience? Feel free to ask them in the chat or raise your hand. First question, what is code translation?
Yeah, we translate the code written in Rust directly to the code written in RISC-V and directly to the machine code, such as x80, x89, 86, 64. Yeah.
Okay, so is this a similar idea to what Zysk is doing with the ahead of time compilation and then the very efficient execution? I'm assuming the answer is yes. Great, thank you. So just to confirm, this is a RISC-V zkVM that AntChain OpenLabs will be launching at some point in the future. Is that correct?
Yeah.
And do you have a rough timeline for when you would release this zkVM?
It depends. Since supporting Java has higher priority for us.
I see. Okay. So once Java has been launched in 2026, I guess you would then launch the zkVM.
Yes.
Okay, understood. Fantastic. Thank you so much for the update, Felix. Next up, we have Ventali. If she's here, it doesn't look like she's here. In which case, we'll move directly to some quick updates that I have on the zkVM tracker. So you may be familiar with this zkVM tracker. It's evolved every single month, if not every single week. And I've added a bunch of things here that I wanted to very briefly walk you through. So the first one is that I've added this QR code in case the screenshot gets shared so that people can find it. Another thing is that we now have a strong, very strong dominance of RISC-V here in this top section. These are the zkVMs that I believe will be able to integrate with Ethproofs in 2025 or have already integrated with Ethproofs. And another update here is that on the verifiers, we have 100% dominance of dual licensing. So RISC-0 very recently moved from Apache 2.0 to dual licensing. And I think this is a fantastic standard to set for the community. We also have another third redacted zkVM, which has been added here. This is from a very strong team, and I'm hopeful that they will reveal themselves maybe in a future Ethproofs call later this year. Again, it's a RISC-V zkVM. On the right-hand side, what I've done here is I've added the provers corresponding to the zkVM. So for example, Brevis is proving Pico, Fermar and zkCloud are proving RISC-0. Actually, this is quite interesting that RISC-0 themselves as a team haven't yet integrated with Ethproofs, but two separate provers, Fermar and zkCloud, have. And here I have a little tracker, the number 9. So we have 9 different integrations with Ethproofs so far, and that spans 6 different zkVMs, with one here at the bottom as well. What I've also done is try and provide a little bit of context as to why I think these zkVMs might not integrate with Ethproofs in 2026. So a bunch of these, for example, have chains that are non-EVM chains, either L1s or L2s. So Aztec, for example, or Cairo, or Maiden. And so I don't think it's a priority for those teams necessarily to integrate with Ethproofs. And then some of these zkVMs are mostly focused on the client side. So Cairo M, where the M stands for mobile, is focused on the client side. Same thing for, I guess, zk Engine, which is focused on low memory proving and folding. And then, there's all sorts of other reasons that I've given to try and explain my rationale. But if you think one of these teams should go in the top section here for an integration with Ethproofs in 2025, do let me know. And another thing that I've added here is this mention of a countdown. So I don't know if you've seen on the Ethproofs website, but we have 2 new countdowns, which we'll have Farah discuss. And basically, these 3 teams, 3 zkVMs, Pico, Zyron, and SPON Hypercube, need to do some sort of a change. Otherwise, they will get delisted by the relevant countdown. And this is a flashback to call number 1, where we had a much less sophisticated tracker than we do now. Okay, that's it from me. So next up, we have Leo from Cysic, who will be talking about GPU and FPGA hybrid proving.
Oh, hi. Can you see,
Yes.
can you see my slides? Okay, yeah.
Yes.
Yeah, so my name is Neil. I come from Cysic. So here I'm introducing doing a very quick intro about Readiness. So Readiness is a hybrid system. It's a combination of GPUs and FPGAs. And for the GPU part, we thank Succinct for sharing the code of the Hypercube system with us. And by a very detailed benchmark on the code, we found some of the kernels, they are not very efficient. For instance, the constraint polynomial evaluation takes about 40% of the time. And also there are so many small kernels, which if you want to launch the kernel on the GPU, then the launch time, the context switching time on the GPU is also very time consuming. And the last, the ping pong synchronization between the CPUs and the GPUs, they say, for instance, the sum check and also the Fair Shamir is also will cause this synchronization issue. So that's why we propose this FPGA plus GPU system. So unlike this GPUs, the FPGAs, they are actually very natural for this polynomial evaluation. You can just evaluate, or you can express the polynomial as the native circuits on the FPGAs, and they are also very efficient for doing some trace generation, hashing, and constraint polynomial evaluation. And also with some dynamic reconfiguration on the microseconds net scale, we can essentially basically map all this probably the bottleneck arithmetic circuits into the real circuit on the FPGAs. Yeah, so that's the first slide. Okay, yeah, so based on this conjecture, we built our onboard. So the goal is to achieve real-time proving, I guess, for at least 95 to 99% of the block. We want to do it for real time, under 10 kilowatts. And the idea is to here is to use our customized FPGA board, which use 7 FPGA chips. So 7 FPGA chips is around, I guess, 1.4 kilowatts. And then we rely on 16 RTX 4090 GPU cards, which cost around 7.2 kilowatts, plus some either for the CPU and also for the memory. So our goal is to achieve real-time proving under 10 kilowatts. So that's our goal. And we are right now, I guess, on the right track towards that. So the goal is to say, for the upcoming quarter, from October to December, we want to integrate our thing with Ethproofs. And we will also open source our bitstring of the FPGAs under dual license. If you want to try it, you can deploy it on this like F2 instance. Yeah, so here is a picture of the board, and we are integrating with our GPU resources to hopefully to get real-time proving under 10 kilowatts in the coming months. Yeah, so that's all.
Perfect. Thank you for the update. I guess I'm curious, if you were to remove the FPGAs and do everything on GPUs, how much slower would the system run?
So that's so right now, to be honest, Venice right now is a pure GPU system, and yeah, we are probably like in the coming months we will first try to achieve it on the GPUs. Probably like it will with like many more GPUs such as like 16 to 32 GPUs, and also for probably like a lower percentage of the blocks. And we are still like benchmarking on all the things, and yeah, we will keep the community updates with our like updates on the real-time proving on that part. Yeah. So right now the FPGA like we use, as you can see, we use like 7 FPGAs, like one VU 1502, like one like 2 VU 47P and one and 4 VU 13P. So that's something like we built this board, we built this customized board with all these FPGAs. And yeah, we will like do this like for the FPGAs, and also we will do it for the pure GPU system. Yeah. So the exact number we will release to the community as soon as we have some concrete and also confident result on that.
Okay, great. And did I understand correctly that you have access to the SP1 Hypercube prover, and you've modified the GPU acceleration? Is this going to be upstreamed in SP1 Hypercube, or will it stay as a separate standalone prover from Cysic?
Yeah, we are right now in discussion with the vaccine team on that part. Yeah, so like we optimize a lot on the GPU prover, and we will probably like first demonstrate our result to the vaccine team. And since like we have access to their code, we want to make sure like we don't violate any agreement with the vaccine team. And after we demonstrate our thing to the vaccine team, we will release to the community. Yeah, on that thing.
Okay, got it. Exciting. I mean, on a single GPU performance, SP1 Hypercube is currently the fastest. And so it sounds like there's even more juice to squeeze that hasn't been integrated thanks to your optimizations. Great to hear. Thank you so much, Leo. I'm not seeing any questions in the chat. Next up, we have Maxime from Nethermind, who will be talking about snarkifying Nethermind.
Hello.
Hello.
Hello. Do you see my screen?
Yes.
Oh, perfect. Yeah. So, yeah. So, I'm Maxim Menshkov. I work at Nethermind. At Nethermind, we have made some progress on zkEVM. So, I will tell you a bit more about it. We have made a few blog posts about zk progress. It's probably better to look through them right now because they have much more information about this topic and contain a bit more about the implementation details. Right now, we have done some work on execution witness. We consider it done. We have made a stateless executor, which is also done. We've made a minimal EVM binary. It works, it's fine. I personally worked on RISC-V 64-bit compilation of Nethermind client. It's also done. I'm also working on Zisk integration. There is some work in progress right now because we have like a few not so big technical challenges to resolve. And also we need to standardize some things regarding all other zkVMs. So we also plan in future to support RISC-V 32 bits if it still will be necessary, and yeah, RISC-0 and SP1. So as for stateless executor and execution witness, the execution witness captures all the state access during block executing, including contract bytecode, storage slots, hash keys, block headers, and all this stuff. And the stateless executor effectively replace blocks using only the witness file without touching disk and network. This work is done by Danish, Nikita, and other Nethermind team members. It's not something I was doing, so I'm a bit less, I can tell you a bit less about it. Then, as for RISC-V compilation pipeline, we built Alpine Linux without some RISC-V extensions. We built .NET without it. We add some B-flat patches to .NET and have a custom compiler based on B-flat. Effectively, in the very end, we have static dependencies, we have no relocations, and we have a binary which is compiled out of file and native dependencies and assembly files linked together in our compiler. That's actually all. Thank you very much.
Thank you, Maxime. Yeah, it's great to see so much progress on guest clients. We started with REVM. We now have Nethermind. We have EVM1, I believe. Matter Labs have their own implementation. And I'm probably forgetting a few. Efrex
from Guess.
Oh yes, Geth, of course, yes. I guess my question to you is related to performance, because you worked on the compilation to RISC-V. Have you looked at the number of cycles it takes to RISC-V cycles to execute an EVM block relative to REVM, for example?
No, I can't give you specific information right now because we are still finalizing some work on it. But at least the performance for .NET itself is quite native because we compile using Microsoft compiler with our additions. We also link to native dependencies, static native dependencies, so the performance must be not bad. Of course, it depends on VMs to execute this needed performance.
Got it. Okay, any questions, feel free to just raise your hand or unmute. If not, we'll be moving to Will. Thank you so much, Maxime, again.
Thank you.
Okay, yeah, so we've been working to just, I guess, get all of Ethproofs Day set up. Had a really nice turnout. Okay, thanks. So just a reminder, Ethproofs Day is going to be happening on the last day of DevConnect, November 22nd in Buenos Aires at La Ruelle. The goal is to really showcase all of the progress that we're seeing in real-time proving. So we received over 60 proposals from speakers, which is fantastic. They're all really great. We went through several rounds of reviews, engaged about 10 different researchers from the zkEVM team, cryptography, rig, protocol architecture. And the goal was to really try to distill the talks down so that they're maximally aligned with the, I guess, North Star laid out in Sophia's blog post about real-time proving in regards to shipping an L1 zkEVM. And so the talks that were selected were done so in service of that. And the format and the structure of it is really just trying to resemble an Ethproofs call. So lots of alpha, lots of content, moving through things pretty quickly. And you can see this is going to be going live soon, but we're going to be starting with some updates from the zkEVM team, from Justin. We're going to have some updates from from the cryptography team. And then a lot of a series of keynotes and lightning talks throughout the day. We've got three different panel discussions, one on real-time proving, one on formal verification and fuzzing, and then a final one that is on who pays the prover, so on prover economics and incentives. And from there, I'll hand it over to Farah, but real quick, we've also been working on Ethproofs v3, and so you'll start to see some improvements to the website rolling out close to DevConnect, some branding that just went out recently, and Farah can jump into that. But if you head over to the Ethproofs GitHub org, you'll see that there's now a link to like a very lengthy product requirements document, and that kind of outlines a lot of the mission statement for the document and the things that we're going to be working on, and they're all outlined on a project board. And you can dive in and look at all these different work streams that we are concurrently working on right now. And a nice little glimpse of the t-shirt that you're going to get if you attend Ethproofs Day. So, Farah?
Yeah, I mean, so we're kind of rebranding Ethproofs, trying to simplify the branding so that this is kind of a sneak peek at the refactor branch that I'm working on for version 3. So we're trying to really simplify things so that we focus the attention on the data that we're collecting and allowing the user to interact with it a bit easier. So we're adding some filtering and sorting and exporting of the data. And kind of we'll start to work on better data visualization so that you can select 1, 2, 3 rows and kind of compare them in the UI, and then kind of simplify the routes and navigation also. So hopefully that will be easier for people to actually work with, like what we're the data we're gathering. So you can go to the next slide. And from an engineering perspective, just for scaling with version 3, we're going to try to simplify onboarding and add a team dashboard. That's one of the big pain points right now, I think, is just a lot of stuff is being done manually. So teams can actually maybe manage their versioning of the zkVMs and their verification keys for in-browser verification and things like that. We need to kind of standardize the hardware. Our cloud instances have become kind of outdated. It's a static snapshot of data for cost. So we need to make improvements to that. We've added monitoring for prover uptime. So we've created some Telegram bots in the status page that, it's kind of surfaced some infrastructure scaling problems that we need to confront, especially if we're going to do, proofs for every block, which we want to do. We're going to continue to make improvements on the in-browser verification. Like I said, we have 2 more to add. So I'm about done with SP1 Turbo, and then I need to finish RISC-0 VM. And then we'd like to make some improvement for external APIs and the documentation there. And then also we're going to be supporting client-side proving benchmarks, which Alex is going to do a presentation on. And then also we're going to be supporting this phase 0 ZK validation effort that Justin is working on. And then you can go to the next slide. And then just as a reminder, we have kind of put up these Ethproof countdowns so that we can kind of hold people accountable, I think, for what they're claiming on Ethproof. So all the verifiers need to be open source by October 26th. So that's in about 29 days now. And then all provers will need to be reproducible. So either open source or provide the binaries to reproduce the prover. So that is, the deadline is December 3rd. And that's about 67 days from now. So at that point, Justin kind of flagged those teams are at risk for being deplatformed. So just this is a reminder.
And hope to see you at Ethproofs Day.
Amazing. Thank you so much, Will and Farah, for pushing this effort forward. We have a new logo as well. It doesn't look like much, but now it's all on one line, ETH and proofs, instead of being on two lines. And I'm hoping that will mean that people spell it properly. So it's meant to be capital E, everything else lowercase, basically a portmanteau of Ethereum and proofs. Nothing to do with ETH, the ticker. It's not all caps. And yeah, looking forward to getting a copy of the T-shirt, even though I won't be able to make it in person. Next up, we have Alex, who will be talking about a potential extension of Ethproofs for client-side proving. Alex is from PSE. Alex, the floor is yours. Okay, Alex might not be here. I see Ali's from PSE. Maybe you could ping him. Okay, we'll move on to Kev then. Kev has a new website to tease. Kev, the floor is yours.
Yeah, hello. Can you hear me? Hello?
Yes, we can hear you.
Cool. Yeah, I don't have any presentations. This is just an announcement to say that the Digital Studio team are working on a zkEVM website. We've given the URL in Justin's slides. And essentially you can visit the website to see the progress towards shipping zkEVM on L1 and the work that our team has been doing to help this move forward. There will be some opinionated takes on there, so take some of it with a grain of salt.
Yeah, thank you, Kev. It literally just came up today, just a few hours ago. There's still a bunch of rough edges, but now we have a dedicated website from the zkEVM team in addition to Ethproofs. I see that Alex Kuzmin is back on. Alex, the floor is yours, if you'd like to talk about client-side proving.
Hey guys, my name is Alex and I'm from the client-side proving team of PSE, which is a part of Ethereum Foundation, and I would like to present you a new initiative that we are about to launch that is called Client-Side Proving Quarterly Report, which is all about benchmarks. So the motivation behind that is that client-side proving is now on the rise, and as we see, more and more proving systems are created specifically to be tailored for low resource devices like mobile phones. We did some benchmarks for zkID project earlier this year and caught some attention of the community, so we decided to continue the effort. But since the landscape is ever evolving, it's not enough to just benchmark something once. We think that it needs to be a continuous effort. So we are planning to do it once every quarter. And also another part of the motivation is that no existing benchmark is exhaustive. So it's a work in progress, but we have already fleshed out most of it. So there is a repository and there is roadmap for the first edition of the quarterly report that we are hopefully we're going to present at DevConnect. And our goal is to help navigate the multidimensional space of trade-offs in zero-knowledge proving systems and zkVMs, because no system is good enough to cover all the needs. And we would like to do it by creating the most thoroughly automated suite of benchmarks. Yeah, I see I'm running out of time, so a couple of other things to notice is that we are going to publish the results at Ethproofs, as Farah said earlier, and we will focus on some specific metrics that are relevant for client side. And our code base will be very easy to contribute to. Like here's an example of Rust harness for your benchmarks, where you just need to override a couple of functions like prove and verify, and the benchmark suite will do everything for you, like measuring statistics and collecting, uploading the metrics. And we also provide the non-Rust harness. So you're welcome to contribute, and that's it.
Perfect. Thank you, Alex. So I guess the concept is to benchmark these cryptographic primitives, right, like hashes and ECDSA that are relevant to client-side proving, as opposed to whole EVM blocks that also have all of the logic around it. Yeah, it's great to see that PSE is focusing exclusively on privacy going forward. It's been renamed to Privacy Stewards of Ethereum. And I'm hoping that very, very soon there will be more announcements related to PSE, including an org chart that will detail all the various teams, including Alex's team, which is the client-side proving team. I'm not seeing any questions in the chat. So, and I'm also not seeing Ventali. So I think we can just move on to the main presentation of today's call, which is from Luca of L2Beat. We'll be talking about native rollups. Luca, the floor is yours. Oh, Kev, sorry, go ahead.
Oh, sorry, I just had one question. When do you think this will be integrated into Ethproofs?
It should be done before DevConnect.
Yeah, we're shooting for
nice.
DevConnect for it to be live on Ethproofs.
There's going to be so much happening for DevConnect. It's going to be fireworks in terms of things that we all ship collectively. Luca, the floor is yours.
Can you see the screen?
Yes.
Okay. So thanks so much for having me. I'm Luca. I do research at Altbit. I've been doing this for the past 2.5 years, mainly doing risk assessments. The risk bits of all the L2s. I've been maintaining the stages framework and the stages assessments for these systems, and I'm very happy now to also work on native rollups on this effort. Before jumping in on native rollups, I think it's really important to kind of remind ourselves why we're at a certain stage and where we're going and why we're going in this direction. So what is happening today is that we have Ethereum that is doing 20 TPS, which is a really low number, and we also have rollups. And we had the need to have rollups for this exact reason, that Ethereum is very slow. And these rollups are now today doing around 300 TPS, which is kind of at the limit of what data availability reports today. But we need to understand why we have this difference, right? And the difference is that of course, we want all clients to be able to verify what's going on in these transactions. We want clients, full nodes, to be able to compute the state. And for Ethereum, these nodes needs to re-execute everything, while for rollups, we have stuff like zkProofs and Ethproofs, right? So, in the same way, I like to say that in the same way that in DeFi, we're getting used to ask ourselves, where does the yield come from when we see crazy numbers? I think in the context of scaling, we should also get used to ask ourselves, where does the scaling come from? Like, what are you sacrificing, if anything, to have this scaling, right? And here, we don't want to sacrifice verification, so that's why we're working on these solutions like zkProofs to be able to maintain verifiability while not doing re-execution, which is the main bottleneck today, right? So we have this new tech, which is zkProofs and Ethproofs, and one can ask themselves, like, why we're not using the stack on L1 directly. And one of the reasons is that the tech was too experimental, it was too expensive, and there was no good way to mitigate bugs other than multisigs. So in a way, zkProofs are too risky to use on Ethereum. So 5 years ago, with the rollup-centric roadmap, we kind of decided, okay, this new tech is very cool. Let's have rollups experiment with this tech. Today, this is not true anymore. Like it is kind of true in a sense, but we're getting more and more confident that we can use this tech on L1 itself, right? So now let's imagine a world where we also have zkL1, zkVM, right? And potentially also let's assume that we scaled DA, of course. So one thing that we can ask ourselves is, okay, if we implement the zk tech on L1 itself, what are we using the rollups for, right? And because previously we needed rollups because Ethereum was very slow. Now if you have zk on L1, also L1 is potentially very fast. So the first reason is that if you think that 10,000 TPS is enough throughput for the work computer, you're not ambitious enough. Potentially, what is Ethereum is able to support is, of course, Ethereum receiving 10,000 TPS, and this number comes from, more or less the limits of serial execution. There is maybe one order of magnitude of uncertainty, but around 10,000 or 100,000 TPS. But DA, the cool thing about data availability is that it is possible to scale it to support much higher throughput than 10,000 TPS. If you do the math with like 1 gigabyte per second, which is something, for example, that Celestia is pointing to, you get around 5 to 6 million TPS that you're able to support. And we believe that no single chain is able to go that fast. And for this reason, you need multiple chains that are running in parallel asynchronously to saturate all this capacity. So ideally, we would have Ethereum that does 10,000 TPS, and then 1,000 rollups doing 1,000 TPS each for a total of around 10 million TPS. And I really like the kind of narrative that zkSync has been using in the past of internet allows for limitless expansion. You can always add more servers, cable, and connections to the internet. And this is kind of the idea that is also here. You can always add another server to the world computer that runs like asynchronously from the others. And then rollups are very cool because they enable custom environments to fit whatever need, right? We've seen rollups with very short block times with super fast confirmations. This is Arbitrum that has been doing this for a very long time. More recently, there has been flash blocks from Unichain. And this is, the customization that brings this is centralized sequencers, right? Which is something that we cannot have on a one that we don't want to have, ideally. Of course, there is some effort to also bring confirmations on a one, but like another type of customization is, for example, in Intmax. Intmax is a privacy chain where you can do private transfers, but they gatekeep the entrance of this rollup with some KYC or AML type of stuff. So this is also something that you can do with rollups. It's very cool what WorldChain did in the past that is also doing today with priority block space for humans that have a verified word ID. This is another customization that you can do. You can have custom gas tokens. This is an example of a chain that is planning to use a yield-based stablecoin. You can have like a Linea, they have plans for native yield for the bridge. You can have custom VMs, of course, at the limit of these customizations, like Cairo, Stylus with Arbitrum, or zkVM with Eclipse. So the rough intuitions behind native rollup is that rollups today need to have a proven system, a dedicated proven system, which is very complex and very hard to secure. It's very complicated, hence is very buggy, and it's very hard to secure. But eventually, as we said, also one will have its own proof system when we move to zk. That will have the same problems, but the thing here is that the Ethereum community will work very hard, of course, to maintain its high quality standards with all the initiatives that we've been talking about, through audits, formal verification, and client diversity. And all projects that are on Ethereum depend on this stack. So there's a clear common interest to converge and make this common stack secure. And then EVM-based rollups that want to stay up to date with new features. They want to stay up to date with each feature, and therefore they need to have upgrades in their own system. But these upgrades are arbitrary. They cannot limit themselves to all the things that Ethereum adds, even though this might be their only need, right? They allow for arbitrary upgrades to increase the risk of users. They need to have exit windows. It gets complicated. It's difficult to get rid of a governing body of the system. So here, the solution is to try to expose, since L1 is already using zk, there is some form of zk verification already happening. You can expose this EVM verification pipeline in a form of a precompile inside the L1 EVM itself. And of course, we want projects to be stage 2. There has been this article by the founder of Facet, which I think is very good at understanding the problems. I kind of disagree on the solutions, but the problem in stage 2 is, of course, there are arbitrary upgrades. So they need to have an exit window. This exit window for stage 2, we said it has to be at least 30 days, but a lot of applications might need to have time locks that are longer than 30 days. You can think about, token unlocks or cliffs and similar. And these use cases will not be covered by the 30 days exit window because you would need to subtract your own time lock, right? So this is also a problem that is present in stage 2. And the only way to solve it today is to deploy something that is immutable, but of course you would lose feature parity with L1. So about the history of the idea behind native rollups, this is something that is not new. In this very nice image by Vitalik, you can see in The Verge at the very end, there is an Explore EVM verification precompile from December 2023. There was also this talk by Justin that I remember attending in zk Summit 11 in Athens, I believe, that discusses native rollups. But there was also a very old GitHub PR by Vitalik in 2017 discussing a execute transaction, a way to just execute one single transaction inside the EVM. And one of the reasons why this was discussed was in the context of Plasma, because also Plasma had the problem of something similar to Ethproofs, and this is by Kelvin that is now working on optimism at OpenLabs, but was previously working on Plasma. And also here they have this need for having something to verify the EVM inside the EVM. So how to implement this execute precompile? So the inspiration here is to use, indeed, the idea here is to reuse the state transition function, the seasonal one. So this is a summary of the execution spec of the execution layer for the state transition. And the way that it works is that it's a simple function that takes as input a blockchain, which is a list of blocks and a block, and applies this block on top of a blockchain. And what this function does is some header checks, and then it executes the blocks. It calculates the new state when you apply this block to the previous list of blocks. And then let me activate the laser. Okay. So there are some header checks at the very beginning. Then you fill this block environment, which is all the field that you need to do the actual state transition. The actual state transition is behind, in this apply body, where the actual body of the block is applied in the sense of the state is calculated. And then there are some post-execution header checks. So the idea here is for the execution precompile to do a recursive call on this state transition, right? So you can imagine the inputs of the execute precompile as if they are passing this information, this block environment information that then the state transition needs. And you should not imagine these fields as they are today, but you should imagine them as if we already have the zkL1 and statelessness. So for example, here, one of the input is the full state. This is like a very big object. You should imagine this as a pre-state, right? And you should imagine this as execution that is in apply body as stateless execution. These transactions are supposed to be the stateless version of this, which are probably traces, some form of traces. But if we have the zkEVM, this is in practice the input to the verifier, to the zk verifier, right? So the idea here is if Ethereum L1 already has a zk verifier that can verify transitions from a pre-state to a post-state, given some transactions, we can also do it for arbitrary states. And these arbitrary states would be the rollup states. And these are some requirements that we want to have in the execute precompile. So as I said, the goal of the execute precompile is to try to do a recursive call to this function with the state of the rollup instead of the state of L1. So what should this execute precompile do? It should properly handle the differences with L1, right? So for example, on a rollup, you don't have blobs transactions. All projects disable blob transactions. So the execute precompile should also try to disable blob transactions. There are some differences, for example, in the way that runDAO works, because it's a value that is kept from the beacon chain, and L2s are not directly connected to the beacon chain. This is also kind of the same with the beacon block root. We're going to discuss these cases in a moment. It should also support L1 to L2 messages. Of course, Ethereum doesn't have the concept of receiving messages, arbitrary messages from another place, but L2s do, right? So this is a difference that we should handle. And an arbitrary, recursive call to the state transition wouldn't handle this, for example. And rollups today, they add custom code to handle this. And we should be able to support this in like a minimal way, right? And L1, L2 messages are used for token deposits. So this is really crucial. And then, of course, you need to go back from L2 to L1 to be able to implement token withdrawals. You should support gas token deposits. So one thing is to send the messages. One thing is to get the gas token on the L2, usually from a token deposit. But it's also something that on L1 is not, doesn't really have this concept, apart from, there is one case, but we're going to discuss it. You should be able to support forced transactions, and it should allow for customization where possible. We really like rollups also because they're customizable, so we should be able to support customization. For example, we should be able to support arbitrary sequencing strategies like centralized sequencing with super fast pre-confirmations. We should be able to support dedicated decentralized networks. We should be able to support base sequencing and any type of sequencing strategy, like proof of governance, type of rotation, or whatever. Ideally, we would also want to support custom gas tokens, base fee collection, for example, right? On L1, the base fee is burned. Most of the L2s, except Linea, which is a notable exception, they collect the base fee. So they do modifications in the client to collect the base fee because this is something that they really want to do. So we should also be able to support this in a way or the other. But the most important thing is that we should try to minimize the diff with the current execution layer. Ideally, everything is inside this precompile. All the other things are left untouched. And also this precompile itself is ideally very, very simple. So let's try to solve these challenges one after the other. So the first that we mentioned is we need to disable burp transactions. We can easily do this inside the precompile, right? So the precompile, you can imagine the precompile having a transaction, this as an input. You can just cycle through them and exclude them. So if you pass something that is a blob transaction, it reverts. This is very nice because all the like opcodes or instructions that are related to blobs would automatically work in the same way that they work for blocks on Ethereum where there are no blobs transactions, right? So like something like blob hash or the blob base fee, they would all be 0 or nothing because there are no blobs, right? So this is something very easy to solve inside the XP precompile. Another thing is RANDAO. So again, RANDAO is something that you get from the beacon chain. The L2s are not connected to the beacon chain. And if you look how the rollups handle these cases, they handle it very differently. So for example, scroll doesn't really support RANDAO. I think it returns just the constant 0 when you try to call it. Arbitrum returns the constant 1. So it's very interesting to see the differences in behavior. Linea returns the constant 2. And can you guess what zkSync returns? zkSync returns this constant for reasons that are behind me. So the only projects that kind of preserves the semantic of RANDAO is Optimism. They have a concept of latest synced and L1 block, and they try to pass over the same value from L1. So they have different behavior, and this is kind of easy to solve because this can also be an input to the execute precompile. This is something that, again, the state transition L1 gets from the beacon chain, and it is in this block environment that we discussed that is passed to the actual apply body. So it can easily be passed as an input, an arbitrary input, which can also be something that you get from L1 and then you pass it. And you constrain, of course, the space of the inputs with a smart contract. Another challenge is how to implement L1 to L2 messages. And this is related to what is called the anchoring problem, which is, in general, how do you get anything from L1 to L2, like any piece of information? And again, this is not something that L1 has. And the way that Optimism and Arbitrum solve this is with a new transaction type. So when you want to send a message from L1 to L2, you send some information on a smart contract on L1. Usually they emit an event. Like in the case of Optimism, there is a transaction deposited event. In the case of Arbitrum, it's a little bit more complicated. It's not just one new transaction type. They have like 10 different new transaction types. But the idea here is, based on something that happens on L1, this new transaction type magically appears on the L2, based on some derivation rule. And instead, there is another set of projects that don't want to add a new transaction type. And notably, there is Linea, which is arguably the most EVM equivalent system. They try not to modify anything, and I think they don't modify anything of the clients running Linea. So they cannot add a new transaction type, which is also what we don't want to do for native rollups. And also Taiko does something similar to Linea. And what they do is, instead of having a new transaction that magically appears when you want to send information from L1 to L2, they have a relayer that sends a transaction with a commitment that represents the messages that needs to be relayed from L1 to L2, and the validity of this commitment is checked inside these circuits outside of the core state transition function. The way that this works in Linea is that they have a permissioned actor that can do this. Because if the value that is passed is not correct, the zk proof will fail. So they would have a liveness failure. Taiko is permissionless. And the way that they solve this issue of passing wrong commitment is that they treat it as an OP. But of course, treating it as an OP is a modification to the EVM that Linea didn't want to do. So they're also like, I guess, working on a solution to this problem. So there are pros and cons to this approach. The pro of Optimism and Arbitrum approach is that contracts on L2 do not need to modify to support cross-chain calls. And I'm about to explain this in a second. And of course, the pro of linear and Tycho is that they don't need a new transaction type. So they have the diff is smaller compared to L1 clients. So what I mean by the contracts do not need to be modified is the following. The way that this new transaction type is implemented is that they don't have a signature on the L2. Because when you want to send a message from L1 to L2, the message can be already authenticated on L1. When you send from L1, you already have a message sender. So on the L2, you can create a new transaction that doesn't have a signature and has the message sender, which is the same as L1, that you already have authenticated, right? So if you send a transaction with your UA, on the L2, a transaction will appear where the message sender and transaction origin is also the same address. So if you implement, for example, a notable contract on the L2, and you want the owner of this L2 contract to be an L1 address, you don't need to do any modification, because when you do a cross-chain call, it already works, right? It will already have the proper message sender in the same way that it works for L1. While for linear, that doesn't implement this, they need to add additional logic to be able to distinguish, to be able to authenticate who sent the message from L1. So you might be familiar with this kind of syntax. This is linear as an example, but if you look at like Optimism, Arbitrum, they implement something very, very similar, which is you need to call the bridge on the L2 side where there is a method that will tell you who is the sender, the cross-chain sender on L1. So as I said, in one case, you don't need to modify. One case is nice because you don't need to modify the contracts, for example, this honorable contract. But the other case is nice because we don't want to add new transaction types. And what I suggest here to do for native rollups is to not add a new transaction type, because this new transaction type is also something that would be available on L1. You would need to have a way to disable it for L1, but allow it for L2. It increases complexity. And as I said, this new transaction type is nice because you don't need to modify the contracts on the L2, but on L1, when you need to go back from L2 to L1, you have the same problem. Because on L1, you don't have this new transaction type. So you have this UX that is maybe better when you go from L1 to L2, but from L2 to L1, you need to exactly implement the same functionality that is here on the screen. So if we implement messages the way that linear works, which is instead of creating a new transaction type on L2, you pass a commitment, and then you provide proofs against its commitment. It's way easier. And there is actually some kind of messaging that is present on L1, which is the messaging that you get from the consensus layer. So you can think about the relation that the consensus layer has with the execution layer similarly to the way that the L1 has with the L2. Because in both cases, it's one layer talking to another layer. And the way that the consensus layer talks with the execution layer is with system transactions. So for example, there is this EIP that saves the beacon block root in the EVM. And the way that this is implemented is that there is a pre-deploy on L1 where these block roots magically appear basically inside the storage of this contract. And we could do the same to solve the anchoring problem, how to pass messages from L1 to L2. Inside the execute precompile, we could add one of the system transactions. So let's imagine that we require these native rollups to have a pre-deploy, which we'll call a anchor pre-deploy at a certain address. And you will pass to the execute precompile an input, which is a commitment, ideally, or a hash of something, which we'll call an L1 anchor. And on the L2, what will happen is that this L1 anchor will magically appear in this pre-deploy. And then the bridge on the L2 side will be able to provide proofs to actually execute the messages. And this is very, very similar to the way that Linea and Taiko already works today. But in the way that this is implemented, it kind of reuses the logic for passing information from the consensus layer, the execution layer. So it's kind of the standard way to do it. I was talking with some people in the past, and as I said before, not many people are using the Beacon. Not many projects are using the Beacon block route on the L2. So some projects were thinking, why do we need to add a new system transaction and a new pre-deploy when we can just reuse the Beacon block route? So instead of on the L2, instead of in the pre-deploy having a Beacon block route, let's pass arbitrary information from L1 that will be used for L1 to L2 messages. And this is maybe, this is open to be discussed, but the thing is, there are some projects that want to preserve the semantic of the Beacon block route. So I would rather have a new system transaction for this, not to overload what is already happening with this other one.
Luca, we have a question from Matt.
Yep.
Because authentication for L2 operations are also based on caller/message sender. Is that a question, Matt? That was an answer. Okay, sorry.
Okay.
So my question is, why again do we need to have the message sender on the L2 be the same as the one on the L1 rather
No,
than
what I'm
having
arguing.
dedicated?
Yeah, what I'm arguing is that we don't need it. So
Okay.
there might be an argument. Like I talked with some projects and they told me, well, maybe like think about adding a new transaction type because maybe we want to have this message sender. What I'm arguing is we don't really need it because first, there are some projects that already don't have these and they work. And when you go back from L2 to L1, you have this exact same problem. You cannot have the proper message sender from the L2. So if you're solving this problem for L2 to L1, why not also using the same mechanism from L1 to L2?
Thank you.
So another thing that we want to support is first transactions. This is something that we require, for example, for stage 1. It's something really important. We really like to say that rollups should inherit censorship resistance from L1, even in the presence of centralized sequencers, right? So, and first transactions are a very complicated mechanism. Like here on the left, I have the way that they work on optimism. It is, again, quite complicated. They have a new transaction type just to support first transactions and messaging as well. And the way that these first transactions are derived is not easy. Arbitrum also adds plenty of new transaction types, including, for example, the unsigned transaction type, which is the second one that is used for first transactions. Taiko at the bottom has this forced inclusion store, which is a contract that is supposed to handle our first transactions in the context of pre-confirmations. And all of them are very complicated in a way. And one way that I think we can simplify, so all of these mechanisms in principle are possible to support with native rollups without any explicit support. Like you would need to have a mechanism to be able to collect transactions, both from the centralized sequencer and from users. And then when you do a state transition, you need to have a way to check that the transactions that the centralized sequencer is sequencing includes the first transactions, right? And this can be done out of band in a way, but it's complicated. All projects prefer doing it inside the state transition function or inside the derivation. And one way that we could simplify all this work for the projects is to use Fossil. So Fossil, what Fossil does is that it gets two transaction lists. One is the inclusion list, and one is the list of transactions from the builder. And inside the state transition function, I showed here on the right the modifications to the state transition function that Fossil introduces. The way that it works is in this apply body, of course, there is this environment of data. There are the transactions, but there is another input, which is the inclusion list transactions. And at the end of the block execution, what happens is this function gets called, which is the validate inclusion list transactions, which checks that the list of transactions that is passed here includes valid transactions from the inclusion list. And this is kind of the implementation of this check. And what I'm proposing is if L1 implements Fossil, native rollups would automatically also be able to access this feature. And they would be able to pass a separate list of transactions that they can collect in a different way other than the centralized sequencer. And the state transition function will make sure that these transactions are included. So, we can call this L2 Fossil. And the full flow of the way that it works is you can force transactions with L1 Fossil on L1. They would be inserted in a queue on L1, and then they would be included on an L2 with this L2 Fossil mechanism through the execute precompile. So this is also one reason to kind of include Fossil in one of the next forks, in my opinion. Another topic is how to do gas token deposits. So yes, we can send messages maybe, but we need to find a way to get the gas token. And the way that OP-Stack and OrbitStack work is that, again, they have a new transaction type that can mint the gas token. In Arbitrum is a different transaction type. In Optimism, it's always the same one. That has also the ability to mint the gas token. A lot of projects have decided not to add this new transaction type like a mint because it's you don't want to have bugs related to this. Notably, Linea, Tyco, Scroll, and also Polygon zkEVM decided not to implement a transaction that can mint the gas token. So the way that users can get the gas token in these projects is using the regular L112 messages. So this is a screenshot from Scroll, the L2 side of the Scroll bridge. And if you look at the balance of this bridge is, I think, max int of something. It's a very, very big number. It contains pre-minted tokens. And the way that you get the gas token on Scroll and also these other projects that I mentioned is by unlocking these pre-minted tokens. So you don't need a new transaction type. You can just unlock from an escrow that pre-mints. So this is kind of, again, a pretty standard way to handle this case. And the cool thing about this is that with this method, it's trivial to support custom gas tokens because to unlock these tokens, you need a message. And what message triggers the unlock can be arbitrary. So for example, it can be an ETH deposit on L1 triggers the unlock of these tokens. Or it could be a deposit of USDC. And in this case, you basically would have a native rollup with a custom gas token that is USDC. Or it could be another ERC20, or it could be an NFT, or it could be some mining mechanism, or it could be a pool of 10 stablecoin. With this method, it's very trivial to support custom gas tokens. And it's very exciting that this is possible to do also with native rollups. So this is also a fun problem to have, which is the first deposit problem. This is a problem that many projects already have. And of course, all the L1 also have, which is if to claim these tokens, I need to claim transactions on the L2, right? But it's the first time that I'm depositing. I don't have the gas, and I'm doing this transaction to get the gas token. So how can I first get the gas token? I need someone else, maybe a relayer to claim this first transactions for me. And there are mechanisms in some projects that do this. or I need to use maybe an internet protocol, but it's kind of weird. So the way to solve this is, first, maybe we don't solve it, because again, this is a problem that exists in other projects. So maybe it is not worth it, since these other projects are kind of doing fine without an explicit mechanism. And by the way, both Optimism and Arbitrum do not have this problem because they have this new transaction type, like I made the gas token. But all the others that I mentioned have this problem. So there is a mechanism that allows to mint actually the gas token on L1. And this mechanism is withdrawals from the beacon chain. So when you withdraw some ETH from the beacon chain, you actually are minting ETH on the EL, on the execution layer. So in principle, if we want to solve this problem, which again is not necessary, but maybe it's nice to have, we could allow another input to the execute precompiler, which is a withdrawal field. And if you look at the way that L1 processes withdrawal, basically it does this by increasing the balance of an address without any action. So this is also something that is, let's say, that could be reused from what L1 already happens. It's a little bit weird to use withdrawals for deposits, maybe. It's kind of an overloading of the mechanism, but something to keep in mind. Another challenge is how to collect fees. So the state transition function in this block environment, again, is passed to the apply body. One of the params is the Coinbase, which is the one that collects the priority fees. And this, again, can be an input to the execute precompile. So there are a lot of inputs, right? And this could be a DAO, this could be a multisig, this could be whatever you want. So there is a way to collect the priority fees very easily. And this is something that, of course, Rollups want to do because it's kind of their business model. And this is an example of, a modification that OpenStack does to collect the base fee. Because again, collecting the priority fees is kind of easy, but the base fee is burned on L1. So if you want to collect the base fee, usually you need to modify the L1 state transition function. And if we can, we would rather avoid it. And there is a very simple way to do this, which is that I found, which is basically a one-line change or two-line change, depending how you count, which is instead of modifying the client to not burn the base fee and redirect them to a multisig, let's say, what we can do is we can count the amount of ETH that is burned and then provide it as an output. So this is a modification that would be outside of the execute precompile, and the only one that I actually found that is needed. But it's very simple because it doesn't modify anything. It just reports in the output what is the amount of fees that have been burned. And then what you can do with this value is that you can pass it on L1, and a smart contract on L1 can, for example, credit this value to a multisig. And this multisig would be able to withdraw this balance from the L1 escrow, because otherwise, if these fees are burned, this would be funds that are stuck in the bridge and no one can withdraw. But if you have this information of how much you've burned, you can credit this amount to one single address. So this is a very simple way to support collecting the base fee without major modification to the client. One big challenge for which I don't have a good solution is that most L2s handle the fee market a little bit differently compared to L1. So the difference between L2 and L1 transactions is that L2 transactions also need to take into account the cost of posting the call data inside blobs. So what these projects do is that they add a new field in the pricing, which is the L1 gas price or the L1 gas used that you can see, for example, here in OpenStack or in Arbitrum or in Scroll. And there are maybe a couple of solutions. So one solution is what Linea does, which is nothing. Simply, they don't have this additional field, but what they do is that they have a new RPC API call that you can do, where it kind of suggests you what is the price that you should set, the priority fee that you should set, so that the centralized sequencer will include you. If you don't pay enough, they will basically censor you. And you might need to go through forced transactions or whatever. But this is intended to be used only for projects that don't pay enough. Sorry, for users that don't pay enough to cover the blobs. Which is, maybe it works, but it's not. Like, there must be a reason why these projects want to add this different transaction fee, right? I tried to look at some new EAPs here on maybe there is a way to solve this problem. One of them is this unified multidimensional fee market that was proposed for inclusion for Amsterdam, which basically adds, this multidimensional fee where one dimension can, for example, be calculated based on another dimension. So you could imagine, for example, if you pass the information of the blob base fee from L1 to L2, you could have a mechanism that kind of conditions the L2 call data dimension based on the L1 blob dimension. But in the way that this is implemented in this EAP, I don't think it works very well. If you look at the way that this is implemented, for example, in OpenStack, it's a linear formula, more or less, a linear relation. But in general, as I said, I don't have a good solution to this problem. But this is also a problem that the L1 zk upgrade will have. Because in the future, when Ethereum upgrades to zk, ideally, L1 itself will use blob, right? And if L1 uses blobs, there's also needs to be this translation between call data that is posted to L1 and that needs to be translated in the cost of posting to blobs. So I have the feeling that this problem will kind of solve itself when the zk team will start to think about how to support blobs for L1. Another challenge is how to support past blobs references. So the way that Rollups work today is that first they sequence transaction, they post them in an inbox, and then at a later time, they prove these transactions, the execution after these transactions. So L1, instead, it's different. When you post transactions, you need to execute them. And with zkL1, it's also the same. That's why we're interested in real-time proving. You post a block, you need to prove it. You post a block, you need to prove it. Here instead, there can be more or less arbitrary delay. And this is needed to, for example, some projects do this because they only want to generate proofs when the ordering is finalized. It might be a risk to prove things before because you might waste some zk proof. But mainly because you want to have one proof for multiple blobs, right? Instead of L1, you kind of have, again, as I said, one block, one proof. In the rollup world, you usually have multiple blocks, one proof. And it's kind of an open question how to support this. If L1 decides to support, for example, recursive proofs in a similar fashion as Mina protocol, where they have just one proof to prove the whole history, maybe it is possible to support this very easily. And also one other constraint, that I wanted to mention that we need to have is we need to know that the data is available when we call the execute precompile, right? And the way that it works for existing rollups is they post blobs, they save the blob hash, and the execute precompile doesn't take the full blob as an input. It only takes a commitment, which is the blob hash, as an input. And the execute precompile has no idea that the data was available because the data availability check is done usually in the inbox, which is another contract. And since we want the execute precompile should know that the data is available because we want to be able to detect bugs. Like let's say there is a bug in ZK. We don't want to allow calling the execute precompile with data that is not available because otherwise we will not be able to re-execute naively and detect bugs. So for this reason, we need to have a way in the execute precompile to be able to reference blobs that are in the past. Not through a blob hash, because again, a random hash doesn't give us the guarantee that the data was indeed available, but something that actually references the actual blob that was available. The blob hash doesn't work here, as I said, because you can only use blob hash in the current transaction and the current transaction environment. You cannot call blob hash in the same way that you can call block hash. It's quite different. So we will need to have a way to support this. But again, I think I don't have a good solution yet. I think it's solvable. But I also think that the way to solve this will become clearer once we get closer to zkL1. So I have a couple of challenges left. This one is whether the execute precompile should do a recursive call to the state transition function or only the apply body. And the difference here is that the apply body, if we do a recursive call to apply body, we can skip the header checks. And the header checks are not really fundamental. Like if you think about the original proposal by Justin Drake that was done in January this year, the way that the interface of the execute precompile was proposed is you have a pre-state root, a post-state root, a trace, and that's it. Maybe guess used, but that's irrelevant. It doesn't have all the information that we usually have in a header, right? We don't have block hashes, we don't have gas used, we don't have base fee. And so one natural question that I had is, I was looking at block access lists, and one of the reasons why we want to have native rollups is that they get the features that their one also has. But if we implement this, native rollups will not be able to get block level access lists automatically because this information is a header information, something that is validated within a header. And this is, kind of the spec that I was looking at, which is you have the apply body here, but the actual check of validity of the block level access list is outside of the apply body, this is the state transition function. So I have a spec for the execute precompile, a draft of a spec, but it's actually two drafts, which is one that uses the apply body. So it only provides the minimal things to do this state transition, and one that reuses the state transition, but also includes the other checks. And it's an open question whether we should use this one or the other one. My feeling is that the state transition one is better because we want to be more similar to what L1 does. And the final challenge is that, okay, we do this recursive call to the state transition function, either it being apply body or state transition, and if anything changes inside the apply body, for example, there is a new transaction type, let's say 7702, or there is a new precompile, or there is a new way to, I don't know, something new inside this, anything, a new instruction, right? All the native rollups would automatically get this upgrade, of course, because it's a recursive call, this function changes, also the one that the precompile uses changes. But the thing is, what happens if this function is updated, like the interface, not inside, but the interface of this function is updated? And you might think that these interfaces do not change very often. For example, the state transition function is super simple. It's a blockchain and a block. Why would you ever want to change this interface, right? And the thing is that it actually does change. In Fossil, you don't have a blockchain and a block alone anymore. You also have an inclusion list. And it is an open question how the execute precompile would be able to support these cases. Like in most cases, maybe it is possible, not to add a new input and just have a default value, which could be an empty, in this case, list. But we might want to support inclusion lists. So it's an open question whether an execute precompile would imply also maybe in the future having execute 1, execute 2, which is kind of ironic if you think about the goal of native rollups. But this is of course only like most of the other changes we would be able to support. And that's all I had. Thanks. I have this book, which you can find at this QR or at this link, where I collected all this information that I kind of explained, with also the draft of the precompile, the spec of the precompile, and more in-depth information about all these topics. And happy to chat if you want to learn more.
This is amazing. Thank you so much, Luca. And I'm so glad that you're championing this and making so much progress. We have Peter that has his hand up. Peter, go ahead.
Yeah, hey, thanks for the great presentation. You mentioned a couple of times that native rollups might incorporate some L1 information, like for random, we might relate the latest random or relate the latest L1 block hash as the anchor. I'm curious if you're talking about non-based native rollups. So in that case, kind of the sequencing is async. The sequencer creates a batch and submits it to the next block, or maybe a couple of blocks later. So by that time, this environment might have changed. In that case, would that invalidate the batch? Would the native rollup fail, or would that possibly change the execution output and invalidating the precomps that the sequencer issued?
Yeah, so the way that I see it is for example, random is a simple input to the execute precompile. So if you're based, you can constrain this input to be the same as the one where you sequence the block in your base block. If you're not based, for example, you can decide not to support random altogether and always pass a constant 0 or a constant 1 or 2, depending on the project. Or what you can do is similar to what Optimism does, which is they don't provide the latest random value on L2, the latest that is on L1. They provide the latest synced value, which basically means that you might have some extra logic when you sequence that maybe collects the random beforehand, or and then like the execute precompile has no constraint on this value. Like this is a simple input, and you decide yourself how to pass it. So if you want to, for example, support preconfirmations, you need to have a way to, and you want to pass the correct value, you need to have a way to check that what you passed was present at some point on L1 as well. But this is again all outside of the execute precompile. If you don't want to deal with this, just pass 0, pass 1, pass 2, pass whatever you want, and the precompile will work.
Jordy's asking, instead of adding a precompile, why don't you just expose the verification key of the zk circuit inside the state transition function?
Yeah, so like the actual way this is implemented in the client, I'm not sure, because also this is very dependent on the way that L1 will verify zkEVMs. So in whatever way L1 will do this, we will use the same exact mechanism. And the difference is L1 will get the pre-state that L1 has, and the native rollups will use the same stack, but with their own state. So if this is done, with the execute precompile or not, Really depends on how zkEVM works. But this shouldn't really modify anything that is said here, more or less.
Right. So there is a world, Jordi, where we have this notion of an enshrined zkEVM, where we pick a single one, and here we would have the verification key basically be burnt into consensus. But there's like previous stages in the shorter and more medium term where some of the validators, if they choose to not run a zkEVM, they can just run it the normal way. And even if you do choose to run a zkEVM, there would be a multitude of them, not just one. And there might be some logic like K of N. So 3 out of 5 or 2 out of 3 would need to agree. And by not enshrining these zkVMs, you can fix bugs, for example, much faster without doing a hard fork. And there's just generally more flexibility. And it's a similar setup to what we have today with client diversity, where the validators are choosing which clients to run.
And this is something that I didn't mention, but there is also a world where we use RISC-V instead of EVM. And you could, in principle, pass as an input the host program. So you could, for example, use the EVM, the host program of the EVM, which would be kind of enshrined in the context of RISC-V. But in principle, you could also use the same zk stack, but with a different host program. And in this case, we would be able to support native rollups with arbitrary execution environments, like arbitrary VMs, which would be very cool. Of course, with some trade-offs.
Can I say something?
Yes.
Yeah, the idea is not to, the idea is to be much less invasive. You just publish the verification key and the clients, they don't need to do anything else. If you want to use this, you just implement in your own smart contract. Your own smart contract, you just read this key, and if you roll up, you just read this key if you want it. And the idea is that you can even have different versions of this verification key, maybe for different zk rollups. So the implementation is very easy. It's just publishing a verification key. It can even be wrong, but the client doesn't do anything else. You just guarantee that in each fork you have a new verification key that theoretically follow the same transition function. But the client, so you need to implement, if you want to use this, you need to implement a smart contract that actually do a verification that actually verifies whatever you want to verify. You verify so you send the proof to the smart contract, and the client only verifies the proof. That's it, like any other proof, but you don't need to do anything else. I think this, as a previous version, as a transition, maybe the final solution is a full precompile, but a good way to start is just putting one key in a state. That's it.
Yeah, I guess one downside of putting one key in a state is that you might not have EVM equivalents. So the L1 EVM might go down one fork, and then if there is a bug for whatever reason in the verification key, then it will go down a different fork. So imagine, for example, if 60% of the validators are running with normal non-zk validators, that's a different situation where 60% are running with zk validators, and they might fork off. Does that make sense?
Yeah, it's just, okay, we can move forward. Just can talk about that.
Sounds good. Alex from Linea is talking about the economics of settling ZKPs. And basically, one of the questions is related to the gas cost of the execute precompile. Is that completely free and handled by Ethereum, or is there a gas cost to calling the execute precompile?
I would expect there to be a gas cost based on the cost of verifying the zkProof. So I would expect the cost to be very, very small. But yeah, I would expect there to be a cost. Like, this is like, in the way that I propose this right now, it's with a precompile call. So you would have a way to price this this call. But again, this very much depends again on the pricing that is also for zkEVM.
Jihoon in the chat highlighted that on October 7th, there is a Fossil session, a Fossil call, which will discuss the intersection of native rollups and Fossil. So if you'd like to join, it's in the Ethereum calendar, public calendar. But you could also message Will or Jihoon. Jordi also had a comment around an elegant way to pass messages where you only send the state root of the L1 to L2s and you store the L2 states in L1.
Sorry,
Jordi,
I missed it.
Do you want to expand on your comment, Jordi?
Oh yeah, I mean, this is a much simple way for all the messaging. Of course, this requires maybe extra work inside each chain. But from the communication perspective, instead of sending messages back and forth, if you just have a way of transferring the state root of the L1 to the L2s, and then the state root of the L2s to L1 that you just store in the state, you can always prove something inside the L2 that you deposit something in L1, for example, or that you send some messages in L1. But the idea is that just passing a single hash, I mean, just passing a single state root of the chain, this is enough. This should be enough for transferring anything. And this is a very simple way. Of course, this adds a lot of work inside the clients because, I mean, you need to, but here with zk, you can also prove whatever you want in L2s regarding L1s. This requires some extra zk extracting, because you need to go through all the Patricia trees, and this has some other complexities for managing the state. But from the communication perspective, this is very simple, and then it's just another parameter, which is the L1 state root that you pass.
Yeah, exactly. So I looked into the way that this works for different projects, and you could pass the L1 state root. So first you need to have the mechanism to pass something, which is I propose to do with a system transaction. But of course, there could be different ways to do it. I think Tycho uses the L1 state root and provides all the Merkle proofs to get the messages, which is kind of expensive, but I would expect also all the work on statelessness to help with this work to make it cheaper and simpler. But a lot of projects pass arbitrary information. Like, for example, Linea passes a rolling hash of the messages, and then on the L2 kind of proves all these messages in the rolling hash. And what I propose is, let's make this as general as possible. Let's allow all the projects to pass an arbitrary commitment and then decide by themselves how to handle this. It could be a state root if they want to. It could be a rolling hash of messages or anything else.
Okay, so we are out of questions. Thank you so much, Luca. I guess if anyone would like to help with this effort, please feel free to reach out. I think at some point it'd be nice to have an EIP, and I believe that Luca hasn't written an EIP yet, so if you're familiar with the process and would like to collaborate, feel free to reach out again. And we're going to need help with tests and devnets and all sorts of other things. So yeah, plenty of work to be done. And yeah, very grateful to have Luca helping out. On that note, thanks again everyone for joining, and see you on Ethproofs call number 6.